It's 2017 and we live in the age of technology. We see major advancements in technology every day. It happens nearly in real time. One place that we are seeing a major push in technology is the automobile industry. Many car companies are striving to create fully driverless vehicles. We have seen some advancements in this region, such as Google's driverless car and Tesla's autopilot feature. While these sort of vehicles are quite the feat of technology and very appealing to the general public, they are of great benefit to persons with a disability, such as blindness or amputees. In the US alone, there are 7 million adults who struggle with some sort of visual impairment. The use of these driverless cars could be the first totally independent mode of transportation for the visually impaired.
Our goal for this project is to create a control system in order to control the velocity of a vehicle while traveling at highway speeds. To do so, it will need to receive inputs that tell the car system the speed limit and therefore the speed it should be traveling. Typical systems measure displacement over time to calculate velocity. Our system is slightly different in that it reads the force on the front of the vehicle by utilizing pressure transducers and inputting this into the pressure equals force over area relation. Since the power of the car is known, this force data is then used to calculate velocity from the power equals force times velocity equation. This instantaneous velocity is then compared to the output velocity in order to make adjustments. By keeping track of and comparing the set allowable speed and the current speed of the car, we will be able to see how well our car is performing.
First, we analyzed a simple mechanical model of our possible system and its inputs and outputs. This setup allows us to focus our system on controlling the speed of a car as it travels on flat ground and when it traverses up or down a hill. Our inputs will receive the total sum of the x direction forces on our vehicle that come from factors such as the weight of the vehicle, the frictional forces of the tires on the road, and the drag and forces imparted on the body of the vehicle. These forces can be used to relate the position of the car with time that will then give us the velocity output. From these relations, an impedance network was developed which ultimately led us to our general form of the transfer function g of s is equal to the 1 over the quantity of ms plus b.
After doing some preliminary research on the cars, we chose to model our system with a mass of 2,500 kilograms to represent a fully loaded medium-sized car and a damping coefficient of 100 newton-seconds per meter to represent the worst-case scenarios such as a car with snow tires, giving a final transfer function of 1 over the quantity of 2,500 s plus 100.
We then plotted the poles from the transfer function to create an initial root locus plot. We see that our only pole is in the left half plane at s equals negative b over m. We then verified the stability of our current system by using a Routh-Hurst array, noting that it will be stable under any positive input since the values in the leftmost column of the array do not change in sign.
Here, we calculated the open loop rise time and settling time. Our current system had specifications calculated to be a rise time of 55 seconds and a settling time of 115 seconds. These are both not acceptable values for the system we are attempting to control. In order to bring these values closer to those resembling a real car, we will be adding a PID controller.
In order to calculate the values of our PID controller, we needed to set some goals for the specifications we wanted our controller to have. The three main specs we were concerned with in our design phase were rise time, settling time, and percent overshoot. We wanted a time delay of less than 2 seconds, a settling time of less than 7.5 seconds, and a percent overshoot of less than 5%. Ideally, we would like to see our system operate with a rise time of no greater than 2 seconds. This will allow the system to respond to any unexpected inputs quickly enough to keep the rider safe, while also avoiding reacting too quickly and potentially causing other issues with manned cars on the road. Since the driverless car is such a new technology, the number of operated cars will greatly outweigh the number of driverless cars. It is important that the driverless cars operate similarly to the other cars on the road. A settling time of about 10 seconds will ensure that our driverless car can safely interact with all other cars on the road. We want our system to operate with a percent overshoot of less than 5% so that the system does not drastically overcorrect and cause issues with other cars, such as a collision. As seen from this root locus plot of the open loop system, this system does not meet our transient requirements.
We had originally done hand calculations on our system in order to determine what type of controller we should use, which was a PD controller, but found out that the constants we had determined actually made our system unstable. Thus, we turned to Simulink to analyze our system and make our controller much more robust and accurate. We began our Simulink analysis by plotting the root locus of our transfer function, g of s, and adding the time domain constraints determined earlier to the plot. This showed that our open loop pole did not fall within the acceptable region and our requirements were not met. In order to remedy this, we added a real left-hand plane 0 to the root locus and began moving the 0 and our open loop pole around until both were in the acceptable region. Our system now satisfied our time domain constraints set earlier. However, we essentially re-implemented a PD controller and our gains were enormous and we had no phase margin. In order to get a phase margin such that we could determine the maximum time delay our system could handle, we then added a real left-hand plane pole to the root locus. We began shifting our open loop pole, real 0, and real pole around until we minimized our gains, had a stable closed loop system, and had a reasonable phase margin. This phase margin ended up being 83.5 degrees, and we can have a maximum time delay of 1.41 seconds. At this point, we had implemented a full PID controller in order to regulate our system. This is good because it allows for a more robust tool to work with if this tool were ever used in different vehicles or altered for fully autonomous vehicles. With this PID controller, all of our constraints, rise time, settling time, percent overshoot, steady state error, etc., were all fully satisfied, our closed loop system was stable, and it was fully capable of performing the controls we wanted.
For our PID controller, we found a transfer function that would meet all the specifications we laid out for our system by utilizing SisoTool and MATLAB. This combination of PID controller elements will allow our system to meet all requirements we have set forth at this point. Since our input of the speed limit will not be time dependent, we are representing our input as a step function, which should accurately model the changing speed limits regularly encountered on a highway. Currently, our step input has a value of 1. However, this could be changed to any speed that the car was required to travel at.
With MATLAB's SisoTool, we determined the specifications of our closed-loop system. With all of our additions to the system, we determined our system had a rise time of 1.74 seconds, a settling time of 2.55 seconds, and a percent overshoot of 1.39%. These specs all meet the goals we had set forth earlier in the design process.
The Siso tool also generated a Bode plot that we used for further analysis on our system. Since our phase plot does not cross 180 degrees, we see that our system has an infinite gain margin. However, we do cross 0 decibels on the magnitude plot, giving us a phase margin of 83.5 degrees, found at a crossover frequency of 1.03 radians per second. Using data from our Bode plot, we generated a Nyquist plot that we also used as another way to verify that our system is closed-loop stable.
From the Bode plot previously shown, we see a phase margin of 83.5 degrees. From this, we can determine that our system has an allowable time delay of 1.41 seconds, meaning it can handle an input signal delay of 1.41 seconds before becoming unstable. This delay is acceptable since our system will be controlled via a computer, of which most possess processing power that can perform all necessary changes well under 1.5 seconds.
Overall, our system accurately represents the necessary system needed to control the velocity of a driverless car. This system exceeded all of the goals we had set forth early on in the design phase. It is simple, stable, safe, and is able to perform all necessary tasks under the given constraints. This design should hopefully change the accessibility and independence a disabled person has in being able to get around on their own. We hope you enjoyed this instructional video on creating a control system for the velocity control for a driverless car.
Thanks for watching!